Okay, good afternoon, everyone. So today we're going to be doing a bit of revision of drawing molecules, right? So it's covalent bonding today, and we're going to be doing some revision. I just realized we don't have them in here, of drawing covalent molecules, and we're going to then go on to looking at the what the effect of type of bonding and structure of molecular covalent substances, right? They're covalent substances made of molecules, what effect that has on their melting and boiling points and so on their physical properties. And we're also going to learn about van der Waals forces, which are really important. They exist between molecules, okay, and they really are in control, if you like, or determine the physical properties. We're also going to look at how to draw line diagrams of covalent molecules, but we're going to start with some revision. So you need your whiteboard. You'll also need a periodic table, just to remember that any covalent substances are made from just non-metals, which are on the right-hand side of this stairs, and not from metals. Okay, so you're going to not see any of these. If these are present in a compound, it means it's an ionic compound. We have already covered that. Okay, so we're going to start the video. Right now, say get your whiteboard. There's some spare pens at the side of my room, just under the window, near the kettle, and there's also periodic tables there. If you need to get one, please get one now.
Hi and welcome back to freesciencelessons.co.uk. By the end of this video, you should be able to describe how electrons are shared in covalent bonding. You should then be able to draw dot and cross diagrams to show covalent bonding. In the last video, we started looking at covalent bonding, so here are two key facts that you need to learn. Firstly, covalent bonding takes place between non-metal elements. Secondly, a covalent bond is a shared pair of electrons. In this video, we're going to continue looking at small covalent molecules. These are really important and you could be asked about them in your exam. Okay, let's start with water, which has a formula H2O. From this we can see that a water molecule has 2 atoms of hydrogen bonded to 1 atom of oxygen. Oxygen has 8 electrons in total, which means that it's got 6 electrons in its outer energy level. I'm showing you the oxygen atom here. Hydrogen only has 1 electron, so here's the hydrogen atom. Now the formula for water tells us that the water molecule contains 2 hydrogen atoms, so here's the second hydrogen atom. As you can see, both hydrogen atoms need 1 more electron to achieve a full outer energy level. However, the oxygen atom needs 2 more electrons. I'd like you to pause the video now and see if you can draw the energy level diagram to show covalent bonding in the water molecule. Okay, so we need to overlap.
Okay, so can you have a go at that now, please? Okay, let's see what the answer is.
The energy levels for the hydrogen and oxygen atoms like this. Now, both the hydrogens and the oxygen have a full outer energy level. Remember that when atoms share a pair of electrons, we call that a covalent bond. So I'm showing you the covalent bonds here. Here are the dot cross diagram and the stick diagram for this molecule.
Just to say, we'll be doing on page 3 and 4, we'll be working through stick diagrams as well. Don't worry about this method. This is really something that I would tend to push at A level. This is the main one that you're going to do, where you actually show the shells, okay?
Okay, the next small covalent molecule is called ammonia, and that has the formula NH3. This tells us that ammonia has 1 atom of nitrogen bonded to 3 atoms of hydrogen. Nitrogen has got 7 electrons in total, so it's got 5 electrons in its outer energy level, and here it is. As we've seen, hydrogen atoms only have 1 electron, and I'm showing the 3 hydrogen atoms here. So again, I'd like you to pause the video now and try and draw the covalent bonding in the ammonia molecule.
Okay, I'm going to pause this for 30 seconds. Okay.
Okay, here's the energy level diagram for ammonia, and you can see that both the nitrogen atom and the hydrogen atoms have achieved full outer energy levels. We can see that there are 3 single covalent bonds in a molecule of ammonia. Here are the dot cross diagram and the stick diagram for ammonia. Hopefully you're now getting the idea that covalent bonding is relatively straightforward. Here's the final molecule in this video. This is methane, which has the formula CH4. That means that a methane molecule has 1 carbon atom bonded to 4 hydrogen atoms. Again, we know that this is a covalent molecule because both carbon and hydrogen are non-metal elements. Carbon atoms have 6 electrons in total, so they've got 4 electrons in the outer energy level, and here they are. Here are the 4 hydrogen atoms, and remember that hydrogen only has 1 electron. I'd like you to pause the video now and try and draw the covalent bonding in the methane molecule.
So another 30 seconds. Okay.
Okay, the carbon atom needs 4 more electrons to achieve a full outer energy level, and each hydrogen atom needs 1 more electron. So they can achieve this by overlapping their outer energy levels like this. And we can see that there are 4 single covalent bonds in a molecule of methane. Here are the dot cross diagram and the stick diagram for the methane molecule. You will find plenty of questions on covalent bonding in my revision workbook, which you can get by clicking on the link above. Okay, we've seen quite a few small covalent molecules so far. In the next video, we're going to look at 2 final small covalent molecules.
Okay, folks, we're going to just watch the next video, which is covalent bonding 3. All right, so it's just more dot and cross diagrams, and then we'll do some more work on that. Okay. Now I'll just get it to play.
Hi and welcome back to freesciencelessons.co.uk. By the end of this video, you should be able to describe how electrons are shared in covalent bonding. You should then be able to draw dot and cross diagrams to show covalent bonding. In the last couple of videos, we've been looking at small covalent molecules. We've seen the molecules hydrogen, chlorine, hydrogen chloride, water, ammonia, and methane. As you can see, all of these molecules have got single covalent bonds. In other words, a shared pair of electrons. In this video, we're going to look at 2 final small covalent molecules. These are oxygen and nitrogen. So let's start by looking at the covalent bonding in an oxygen molecule. This has the formula O2. So in this molecule, we've got 2 oxygen atoms bonded together. Oxygen atoms got 6 electrons in their outer energy level, and I'm showing you them here. I'd like you to pause the video now and try to draw the covalent bonding in an oxygen molecule.
Another 30 seconds. Okay.
Okay, so each oxygen atom requires 2 more electrons to achieve a full outer energy level. And they can do this by overlapping their outer energy levels like this. Now, you'll notice that this is a double covalent bond because we've got 2 shared pairs of electrons. Here are the dot cross and the stick diagrams for the oxygen molecule. Okay, here's the final small covalent molecule. This is the nitrogen molecule N2. As you can see, nitrogen atoms have got 5 electrons in their outer energy level. I'd like you to pause the video for one final time and try to draw the covalent bonding in a nitrogen molecule. So as you can see, each nitrogen atom requires 3 more electrons to achieve a full outer energy level.
Okay. Right, it'll start it now, 30 seconds. Okay, let's see did you get the right answer?
And they can do this by overlapping their outer energy levels like this. This forms a triple covalent bond because we have 3 shared pairs of electrons. Here are the dot cross diagram and the stick diagram for the nitrogen molecule. You'll find plenty of questions on covalent bonding in my revision workbook, which you can get by clicking on.
Okay, folks, I'm just going to close this and then we're going to move on to page 3 of your notes. Okay, I hope you found that helpful and just practice all of that quite a lot. It's easy to forget how to draw them, right? It takes time before you can do it really quickly, but the more you practice, the quicker you'll get. Right, so I'm going to share my visualizer now. Okay, so we're on to page 3. Now, there's a few key things that you just need to bear in mind in terms of learning, right? So if you were to put together a little revision, summary, or whatever, just be aware of the key terms that come up. So, and some of them came up in that video, right? So there's the idea of, there's a definition of a covalent bond, right? That is a shared electron pair or shared pair of electrons. Okay, so that's what a covalent bond is. And then you have 3 types that we've met. You have a single covalent bond, you have a double covalent bond, and you have a triple covalent bond. You can have quadruple as well, but not really beyond that, unusual. Double covalent bond and a triple covalent bond. So those definitions are related to the definition of covalent bonds, right? So obviously if covalent bond is a shared pair of electrons, a single covalent bond is 1 shared electron pair, right? A double covalent bond is 2 shared electron pairs. And a triple covalent bond is 3 shared electron pairs. So look out for those. And remember, a shared electron pair is where you have 1 electron, right? Each atom in the covalent bond, right, is going to put 1 in each. So you have 2 electrons here, 4 here, and 6 here in the shared space. Okay, I know in that diagram he had drawn the shared bonds on the shells. That's okay, as long as you have the correct number, right, and in the correct place, right, either in the sort of shared space right in between them, or on the shells, but not nowhere else. Okay, right. So there were key ideas. Now, another key idea that you're going to have to get used to is the idea of a molecule. Now, I have to say, I think there's always a little bit of confusion with molecule, and just we're going to compare the definition of molecule to compound, because I think the two of those get mixed up, even at A level. I did test A-level boys and they were confused about the difference between them. So if you look at page 3 of your notes, right, you'll see the definition of a molecule. Let me just pull down there. Okay, so 2 or more atoms covalently bonded. So 2 or more atoms covalently bonded. Now, if anybody can recall the definition of a compound, and I think we met it in the atomic structure, I think, my memory is fading. A compound is two or more elements chemically bonded. Now, I just want you to be very clear, or at least start to get your head around the idea of the difference between these. So you can see what they have in common and why there might be confusion. They both talk about two or more, and they both talk about bonding, right? So, but there's the world of difference between them. Some molecules belong to compounds, right? But not all compounds have molecules. Not all molecules are compounds. And we'll see what I mean in a minute. So here you're talking about atoms. Now, remember, well, atoms are just bits of elements, right? The tiniest particle of an element you can get, right? So atoms, so these could be the same or different. Now, if they're the same type of atom, then you have an element. And if you have different types of atoms, you have a compound, right? Whereas over here, the elements, this chemically here, they could be ionic bonds or covalent bonds, right? They're not specifying. That's why it says chemically, it could be ionic or covalent. So I'll give you an idea of this. So you're going to put in, let's do a little Venn diagram. A little, that's too little. Okay, so you're going to do this along with me. So over here, we're going to have molecule. And over here, we're going to have compound. And anything that belongs just to one and not the other, we're going to put right separate. And anything that's both goes in space. So I'm going to give you the first one. CO2. Now, is it a definition of a molecule from what you've seen? It consists of two or more atoms, 3 in total. They are covalently bonded because they're non-metals. So it's definitely a molecule. Is it a compound? Does it contain 2 or more elements chemically bonded? Yes, it has carbon and oxygen. So it actually goes in the middle here. It's both of them, right? What about hydrogen? Right, that was, it's a molecule, right? It consists of 2 or more atoms covalently bonded. Yes, but is it a compound? Are they different elements? No, right? It's an element. So actually, that would go here, but it's not a compound, right? So anything in here is going to be elements. Now, what about this one? NaCl. Okay, so is it a molecule? Right? Is it covalently bonded? No, because it's a metal non-metal, so it's ionic. So it's not a molecule, can't go in here. Is it a compound? Does it contain 2 or more elements chemically bonded? Yes, it does. They just have to be ionic. So NaCl goes over here. I will do 2 more. What about O2? Okay, so O2 is, let's see, what is it? Is it a molecule? Yes, right? It has covalent bonding. Is it a compound? No, it has only one element, so it's going to go in here. And what about, let's do 2 more actually, magnesium oxide, and let's do, okay, MgO. Doesn't qualify as a molecule because it doesn't have covalent bonding. Does qualify as a compound because it has 2 or more elements. And last one, HCl, right, does qualify as a molecule because it's non-metal, so covalent bonding. Does qualify as a compound because it has 2 or more elements, so it goes in there. Okay, so just wanted to take a little time out for that because I know that causes issues. Okay, so back to our notes. Right, so you need the definition of a molecule. Just get my highlighter. Learn that. And just make sure, maybe put beside it the definition of a compound so you don't get the 2 of them confused, okay? Just to remind you of the definition of a compound, 2 or more elements chemically bonded. So just make sure you identify, even though they sound so similar, they're so different, right? A diatomic molecule is a special type of molecule that has only two atoms in it. Okay. Now, if anything is made of molecules, then it has to be covalent bonding. Just by definition, molecule contains covalent bonding. If you look at the definition, right? So now, what about the nature of the covalent bond? That's really what we're going on. Well, actually, we'll come back to that. We'll come back to that because what we're going to do is we're going to just have a little revision of all the molecules we've met so far. So we're going to have a look at the line diagrams. Now, we've already actually encountered these a few times, so let's see if you can apply them again. Right, so I'm afraid this table seems to have printed dodgily. Okay, so the first one, right, we're going to list all of the elements that we've met, compounds, all of the molecules that we've met. So if you want to just copy these down, the next one I have in is water, which is H2O. And then I just did them in order of the way they were done on the videos there, but you can do them in a different order. Then we've got ammonia, NH3, methane, CH4, hydrogen, H2, chlorine, Cl2. They were in the first video on Tuesday. Hydrogen chloride, HCl. I'll just rewrite that, HCl. Nitrogen, which is the chemical formula N2. And one that wasn't actually in the video at all, but we need to know, is carbon dioxide, which is CO2. Okay. So I'll give you 30 seconds just to copy those in. So just a reminder that water. Okay, I think I'll give you another 30 seconds. Okay, I hope you can see this. Actually, I'm going to switch over to black pen because I know my projector is a bit rubbish. Okay, so hopefully you got that. Right. Now, what you're going to do, and we'll just do the first couple together, is we're going to decide whether it's a diatomic molecule or not based on the definition. So it'll be diatomic if it only has two atoms in the molecule. So oxygen counts as diatomic because there are only two atoms in the molecule. And then the line diagram is O, double line O, and remember the two lines represents two covalent bonds. And two covalent bonds means two shared electron pairs. So remember, the covalent bond is a shared electron pair. An ionic bond is the electrostatic attraction between opposite charged ions. Covalent bond is a shared pair of electrons. So they're very different, right? They both involve some kind of, they're very different. Okay, so water, let's do water together. First thing, is it diatomic? Nope, it has three atoms in a molecule, so it's definitely non-diatomic. And how we draw it is HOH. Okay, now you might see it like this. That's only kind of because that's the shape of it, but you don't need to know that, right? As long as you have as long as you show the atoms correctly attached to the correct atoms and you show two single covalent bonds, an examiner would be happy. Okay, so how about trying, right, I've got water again on the next page. How about trying the rest of these yourselves? See how you get on. All right. So you want to identify, is it diatomic? And the next thing you want the line diagram. Okay, I'm going to give you a couple of minutes to do that. Okay, let's see how you get on. Right, I'm going to zoom in again so you can all see. Right, so let's start with ammonia. Okay, so ammonia diatomic, no, right? Has 4 atoms in the molecule, and the line diagram, so it's got nitrogen in the middle, and then it's got 3 single covalent bonds, hydrogens. Okay, methane is not diatomic. It has 5 atoms in a molecule, and it has the carbon in the middle and 4 single covalent bonds to hydrogen. Right. Hydrogen, yes, it is diatomic. It has 2 atoms in the molecule. Yes, and they are single covalent bonds, so the line diagram will look like that. Chlorine is also diatomic. It has 2 atoms in the molecule, and they are singly bonded to each other, like that. Hydrogen chloride, by the definition given by CCA, it is diatomic, although I have to say diatomic normally refers to the diatomic elements. But anyway, it has 2, it qualifies as diatomic. Compounds generally aren't considered diatomic, but let's not go there. Okay, so it's a single bond between the hydrogen and chlorine. Nitrogen is diatomic, has 2 atoms in a molecule, and this time you've got a triple covalent bond between the nitrogen atoms, which you represent like that. And lastly, carbon dioxide is not diatomic. It has 3 atoms in the molecule, and if you refer back to your notes, right, you've got 2 double covalent bonds on either side. Now, these notes don't contain the dot and cross diagrams from the electron energy level diagrams, did we? We mean dot and cross diagrams where you include the outer shell. Now, you can put them in your notes if you want, or you can find them. They're all in the revision guide, and they're all in the work that we've done so far. So I suggest at some point you sort of assemble to one page, right? All of the dot and cross diagrams and the line diagrams. You could even maybe add them in here, right? They would fit quite nicely here. So for example, if you were to include the carbon dioxide one, right, you'd have carbon, oxygen, oxygen, dot cross, and then the lone pairs on your oxygen. So remember the idea of bonded lone pairs are these guys here that don't go into shared space. Okay, so you might want to do that when you get a chance, is include dot and cross diagrams for all of these as well. Right, now we're ready for the next section. Okay, get rid of that. Which is, we're going to go back to page 3, right? And so we're going to look at the nature of covalent bonds. Now, they're really pretty interesting, and you may not think that yet, but you will. Okay, so you've got two types of bonding covalent substances. Just be aware that covalent bonds are strong. Now, it may not appear like that when you see the properties of hydrogen gas and so on, but it is true. It takes a lot of energy to break a covalent bond. It takes a lot of energy to separate that shared electron pair. But there's another type of force that comes into play, which is called the van der Waals forces. These are forces that are between the molecules, and they are very weak. All right, now I think I've shoved that little line in there. But we are going to now click over to page 5, because we're going to talk about the structures of substances composed of molecules. Now, just a quick, because I'm going to show you a video on this. So I want you to be aware that when it comes to bonding, you have two aspects to bonding. You have bonding and you have structure, right? So the bonding is the ionic bonding, the electrostatic attraction, or it's the covalent bonding, the shared electron pairs, and there's a third one we're going to look at, which I'll mention, which is metallic bonding. Okay, so you have three types of bonding. And that's really talking about the connections between the atoms or ions. That's the bond. It's actually what's going on between individual atoms or ions. So for ionic bonding, it's the electrostatic attraction between the ions and their formation in the first place. For covalent bonding, it's the shared electron pair. But then we have sort of the macro, the structure. If you look at lots of atoms or ions, you will see the structure of them, right? You know, the sort of bulk, kind of lots of them together. Now, for the structure for ionic, if you have ionic bonding, if you refer back to your notes, you get a giant ionic lattice. And remember, that was lots and lots of cations and anions spread throughout this huge three-dimensional structure, and everything's held together by strong electrostatic attractions, but it's this giant crystal. In covalent bonding, you can have two different types of structures, right? You can end up with molecular covalent structures. In other words, covalent substances made of molecules. Or you can have giant covalent, but we're not going to look, and that giant covalent only has, right, well, we'll look at that afterwards. They're very different. Both got covalent bonding. Molecular covalent structures are very different to giant covalent structures. Okay, so that's what we're going to look at now. So we're going to show the video first, right? Because I think the video is pretty good. And we'll look at the notes. Done that. And
Hi and welcome back to freesciencelessons.co.uk. By the end of this video, you should be able to explain why small covalent molecules have got low melting and boiling points. You should then be able to explain why small covalent molecules cannot conduct electricity. In the last few...
Can we just change here he's calling it small covalent molecules, but I think I want you to think of it in terms of molecular covalent substances, right? So substitute in your small covalent molecules for molecular covalent substances.
Videos, we've been exploring covalent bonding and we've seen lots of covalent molecules, and I'm showing you them here. Now, one key fact about all of the covalent molecules that we've seen is that they are small. Even methane, which is the largest, only has 5 atoms. There are 2 key properties of small covalent molecules, and we're going to look at these in this video. I should point out that the first property can seem a little bit tricky, so let's get started. So the first key property of small covalent molecules is this. Small covalent molecules have got low melting and boiling points. This means that they're usually gases or liquids at room temperature. This shows you the melting and boiling points of all the small covalent molecules that we've seen so far. As you can see, they all have very low melting and boiling points. All of the small covalent molecules that we've seen are gases at room temperature. Now that's because they all boil at temperatures below room temperature. Now there is one exception to this, which is water, which I'm showing you here. Water is a liquid at room temperature, but it still has a relatively low boiling point at 100 degrees Celsius. In the exam, you could be asked to explain why small covalent molecules have got low melting and boiling points. Let's look at that now. Okay, this shows a number of hydrogen molecules in their liquid form. So this would be a very cold temperature. For example, minus 257 degrees Celsius. Now, I'm using hydrogen to illustrate this point, but this equally applies to the other small covalent molecules. You can see that the molecules are vibrating. I should point out, because it's a liquid, these molecules would also be moving from place to place, but I'm keeping it simple here by just showing the vibrations. Now, there are 2 key ideas that you need to understand. Firstly, the atoms in each molecule are held together by strong covalent bonds, and I'm showing you that here. Secondly, there are very weak forces between one molecule and another molecule. Scientists call these intermolecular forces. Intermolecular means between molecules. Remember that intermolecular forces are weak.
Now, just to note that, I'd say this is for an English board, you need to know the name. There are a few different intermolecular forces. You need to know that this one is called a van der Waals force. We'll see that in your notes anyway. So it's weak van der Waals forces.
Now, as we increase the temperature, the vibration of the molecules increases. At a certain point, this vibration is strong enough to break the weak intermolecular forces holding the molecules to each other. At this point, the molecules turn to a gas. In other words, they boil. So, can you see that because the intermolecular forces are weak, it does not require very much energy to turn small covalent molecules from a liquid to a gas? In the exam, you could be shown a small covalent molecule and asked to explain why it has a low melting and boiling point. So the key fact is that there are weak intermolecular forces between the molecules, and these do not require a lot of energy to break. Now, there is one further point. As we increase the size of the covalent molecule, the intermolecular forces increase. We can see that with this table. This shows the first 5 alkanes. Alkanes are also small covalent molecules, and we're going to see them in a lot more detail in later videos. We can see that as the alkane molecules get larger, their boiling point increases. That's because the intermolecular forces increase and require more energy to break. Okay, so we've seen that small covalent molecules have got low melting and boiling points. So let's take a look now at another key property. Small covalent molecules do not conduct electricity. That's because the molecules do not have an overall electric charge. Again, this is a relatively common exam question, so it's really worth learning. You'll find plenty of questions on the properties of small covalent molecules in my revision workbook, which you can get by clicking on the link above. Okay, so hopefully now you should be able to explain that small covalent molecules have got low melting and boiling points. You should then be able to explain why small covalent molecules cannot conduct electricity.
Okay, folks, so that's really a lot of what we need to know for this next section is in that. So it's just a case of going to your notes and having a look at the relevant parts. Now, as I say, some of the terminology he used, we have to change slightly. So we're not calling them small, what do you call them? Small molecules, small covalent molecules. We use the term molecular covalent structures, right? So let's see. So we want to use this term, okay, instead of small covalent molecules. And sometimes they're called simple covalent structures. Used to be in the exam board years ago, but they've changed it a bit, okay? They all mean the same thing. Okay, so they're substances made from molecules, and let's see, they're all the substances we've met so far in this booklet, like oxygen, carbon dioxide, methane, ammonia, and so on. They're all made of molecules. Now, the key thing is that between atoms, you have strong covalent bonds. Now, strong bonds require a lot of energy to break. So to be honest with you, in terms of the properties here, these bonds don't break. They'll break during chemical reactions, but just in general, everyday, going about their business, turning from solids to liquids to gases or whatever, these bonds stay where they are, right? Your molecule will remain a molecule. What determines the properties is the little connections between the molecules. So there are weak connections, weak attractions between the molecules called van der Waals forces. Now you need to know that. So they're weak, right? And they're between molecules. So they are intermolecular forces, what he mentioned on the boards, on the video. So they are, van der Waals forces are a type of intermolecular force. In other words, intermolecular being between molecules, right? It's just a fancy word for that, fancy sounding word for that. Okay. I'm sorry about the scribbles. Okay. Now, you need to know that you need to use that idea of strong covalent bonds and weak van der Waals forces to explain the properties of molecular covalent substances. So I've summarized here. Now, as I say, I've got in the box the specification. So there's only certain properties that you need to explain, and actually they're the same for ionic and covalent in terms of the properties. So you need to explain, you need to state whether the boiling points and melting points are high or low for most of the structures, and you need to state whether they conduct electricity or not. Okay, and you state whether they dissolve in water. So let's have a look at the physical property. So for molecular covalent substances, they have low melting and boiling points. Now that's as opposed to ionic, which had high melting and boiling points. And why? The why is very important, okay? So make sure in an exam question, you know, are they asking you to state a property or explain a property? So the why, they have weak van der Waals forces between molecules and they require little energy to break. So the less energy it requires to break bonds, the lower the melting point and boiling point are going to be. So the connection here is weak and little energy, right? They do not conduct electricity. And recall that ionic compounds will, if they are molten or aqueous. Covalent compounds do not, or sorry, covalent molecules, molecular covalent substances do not. Reason, there are no charged particles. There's nothing with an electrical charge that can move and carry charge. Now, in ionic compounds, it's the ions that carry charge, right? And as you'll see, in metals, it's free electrons that can move and carry charge. Metals and also graphite, which we'll meet next week. Excuse me. And they are generally insoluble in water, and you don't need to know why, you just need to state it. So what I'd like you to do now is there are some questions on page 6 of your notes, right? So there's a little bit of extra information there, and I want you to complete page 6 and to the top of page 7, right, to here for Tuesday. Right, so complete it in class and or for homework. Right, thank you.